So I'm Kadi. I'm a senior React Native engineer at Formidable. You might have heard from us from products such as Urkel or Spectacle, or thanks to Catalan's shout-out victory, or from some colorful individuals representing us in previous conferences. My experience with native development actually started, well, my very first experience was in 2014. I had to dig this out from LinkedIn. When I was a junior analyst programmer at a data science company, and I was exploring different things to do other than MATLAB. And one of the things I tried was native Android development. And so I did this course in Coursera, thought it was quite interesting. I finished it, got a certificate, added it to my LinkedIn, and forgot all about it. And I became a web developer doing JavaScript. So as things had it, though, I went all the way around to native, and now I am a web developer that writes native apps because we can do it in JavaScript. So I'm just going to, the goal of my talk here is just give you some general security considerations. Security is, we all say that security is important, and it is, but it's not the first thing we think about because it's not very fun. And we don't really get punished for having bad security most of the time. You only regret it when things go wrong. So here are just some things to, I guess, look into, remember, so that you don't make the same mistakes that other people have done. So the first half of my talk is going to be about secrets and how to keep them safe. So when it's for these secrets, I mean things that the user shouldn't see. So things that both the user using your app shouldn't see and any other third party shouldn't see. So here are some general rules. If the user shouldn't see it, do not send it via network request, do not ship it in the app code, and do not save it in Acing Storage. Now, some of these things probably might be common knowledge for you, and some of them aren't. I'm going to go through all of them and just give you some examples of why you should pay attention to it. So a month or so ago, there was a news story about this dating website called 3Fun, a dating app called 3Fun. And they're an alternative dating app, kind of like Tinder. They have like location-based searching and matching, so you can match the users that have the same interests as you. And what was found that if you were to inspect the traffic of that mobile application, they actually send everyone's sensitive information to every other user and just hiding it in the front end. For example, everyone's real-time location. Now, this is a huge invasion of privacy at like most of the time, but when it's a dating app, that's a little bit alternative. You don't want your boss to know. That's the last thing you want. But it gets worse. They also send private photos. So the user's object has a key for private photos, which are a bit sensitive, and they are filtered out on the front end based on the user's preferences. But obviously, if you just look at the network request, you can see it immediately. So that's embarrassing. And now you might be thinking, well, that's pretty obvious. Obviously, I'm not going to do that. That's never going to happen to me, right? Well, it kind of happened to me, so don't judge. So here's an example of an actual thing I was working on. So we had an app that had a bunch of users, and users were able to see other users on the app. Now, each individual user can set their privacy settings on their profile. There were 3 settings: public, protected, and private. So this is like a crude rendering of a design that I was given. So public users, you have their avatar, their name, some interests, a bio. Protected users, just the avatar and name, and for private users, we display nothing. They don't even get returned from the API. Now, this is the data that I was given. So I didn't build the API. The API was already existing. They were using it for a different application. So for a public user, we get all the information that is stored for the user, including their name, their interest and bio. For the protected user, we get just their name and the avatar. And then, as you can see, for the private user, they don't even get returned from the API. Now, you've probably already seen the problem, that if the user is public, the API also sends their email and phone number. So we don't display it in the front end, but it does get sent. And now the thing is that I didn't question, because I was like, oh, it's not my problem, I didn't build the API. What I should have questioned is, should the API be sending that? Like, is that a thing that we want in our app? Do you want to have consequences for that? And I didn't. So that was embarrassing. But it wouldn't have been embarrassing if we didn't get caught. However, as it happened, one of the users of our application was a bounty hunter for security flaws. So the first thing he did, opened the app, looked at the network traffic, and was like, yep, look at that, I can see everyone's emails. Emailed it to us, got a reward. So yeah, don't do that. So the link from this sensitive info should always be filtered server-side. But from this experience and from wanting to have interesting content for this talk, I was wondering, how easy is it really to see your mobile traffic? Like, it's not trivial. Like, it's not like I can double-click on the app and see all traffic. But you can do it on the web. So how easy is it on the mobile? And they've been able to do it. So I had to go, and you should too. Like, not right now, but later. I think it's quite fun. So all you need is a phone, a laptop, a proxy app, and Wi-Fi. I used an old iPhone, like just in case, and this MacBook Pro, and Charles Proxy, and just my home Wi-Fi. So these are very high-level instructions, because I don't think anyone's going to use these slides to actually set it up, but it's all available online on Charles Proxy website. So what you need to do is install Charles Proxy on your laptop. You configure your mobile traffic to go through the proxy. So all you need to do is connect to a Wi-Fi, the same one your laptop is connected to, and then scroll all the way to the bottom. It says proxy, and then you add your laptop IP address, and then port 8000, which is a Charles Proxy app. And what this does, it makes sure that it sends all your network traffic through Charles Proxy, and then Charles Proxy sends it to the web. And then lastly, if you want to actually see the data, because almost all data is protected by SSL, you need to also install the Charles Proxy SSL certificate in order to actually decrypt it and see it in plain text. So in order to do that, you get some scary warnings saying, are you sure you want to? Because this is self-signed. You say yes, but if you use your actual own phone, make sure to actually uninstall those when you've finished experimenting. So there's some links in the bottom if anyone's interested in trying this out. This took me about 20 minutes of Googling start to finish, and I was in. I could check out my apps. So here's Slack. We can see some API calls. I can see some responses. I thought I was like, OK, this is quite cool. I tried Facebook and Instagram, which actually won't work with this particular method because they use SSL pinning, which means that they actually check that the SSL certificate is not self-signed, so I wasn't able to do it. There are other ways around it, but that would make this talk much longer, so I'm not going to go into that. I looked at LinkedIn, which was fun. You can all make yourself feel a bit better by looking at their API structure. And I looked at Virgin Active. So if you don't know what Virgin Active is, it's a gym in London. It's a gym that I go to. And they've got this tiny mobile app, which you mostly use just to do bookings, like you book to a class. So it doesn't do a lot. But the structure is more similar to smaller React Native applications that you would do for work. And if you look at the requests, outside of the weird club/club and booking/booking thing that they also have an auth/auth call. So I was like, OK, that's interesting. What's in here? And it turns out that is the call that they use to take the stored refresh token and exchange it for an auth token. And I could see the auth token. So I was like, OK, that's interesting. What would happen if I put it into Postman? Well, this happens. It's just an API. I can explore my Virgin Active API easily with my auth token. Now, this is not a security concern. This is just a thing you can do, but it surprised me how easy it is. And it's just a reminder that even though you're building a mobile application and it feels more closed sourced, it's not really. It's just as open as a website. Now, moving on. Do not add sensitive info to your app code. Now, we wouldn't do that on a website anyway. And when I say sensitive info, I'm talking mostly tokens. And some people have learned this the hard way by adding a AWS token to the open source project and then found someone mining Bitcoin. So how hard is it really to get sensitive info from your app source code? Well, it's harder than what I've just showed you with the network request, but meet Jane Wong. If you don't follow her on Twitter, I would. I find her tweets quite entertaining. So she is a Hong Kong-based security researcher. I think that's what she calls herself. And basically what she does on her spare time is she looks at security flaws in applications, and she finds out unreleased features that popular apps are trialing. So apps like Facebook and Instagram and Twitter, before actually rolling out a new feature to all of their users, they add it to the app code and put it behind a feature flag so they could test it. Right? So some of the recent examples that I found in her Twitter in the last month was Facebook working to hide like counts, Instagram working on comment sharing, and then this rather cool example of Twitter allowing you to subscribe to threads without actually replying. And she found that 147 days, so almost half a year before it was actually released. So that's pretty cool, and she doesn't work in any of these companies. So you might be wondering, how does she do it? And it's as low level as you might expect. She seems to be on an Android phone, so what she does is she gets the APK for the app. She decompiles it using a public tool and a custom Python script, which she didn't specify what it does, but presumably some kind of diffing. And then she just reads through the code, which she admits is often quite low level, to figure out what's changed and what's hidden. So I think it was pretty amazing that you can do that, but this just goes to show that anything you put in your code is not secret. So all those embarrassing variable names, she might see them. Now let's move on to Acing Storage. I think we've all used Acing Storage, and I think this sentence, I think I took that from the React Docs website. So Acing Storage is a simple, unencrypted, asynchronous, persistent key value storage system that's global to the app. And you should use it instead of local storage. And I agree, you should, most of the time. So use it for non-sensitive info. Yes, you should use it for your persistent Redux state. Yes, you should use it for your Apollo cache, but you should not use it for your auth token. That is because, as it said, Acing Storage is completely unencrypted. It's literally a file in your documents folder that you could plug your phone in, and you could inspect it and see what the tokens are. And one of the good things about Acing Storage is it works the same way as local storage. So it's sandboxed for each app. So for example, if you have my Facebook app wouldn't be able to read my Acing Storage for my Instagram app, and vice versa. But it is an operating system restriction which can be overcome. So these rules that we tend to rely on aren't hard set for phones, because if you think about what a phone is, it's just an operating system with certain features and restrictions set by Apple and by Android. So you might have heard of rooting or jailbreaking devices. So they basically mean the same thing in both of the in iOS and Android. So rooting is on Android obtaining root access to the device. So Android is Linux-based, and you basically have a user that has certain access privileges. You couldn't just change Android source code, but you could root your device, which means you can get access to the root user, which means that you can do pretty much anything, including reading the Acing Storage data from other apps. And the same thing for iOS is called jailbreaking. It pretty much does the same thing. It's privilege escalation of Apple devices. So you could remove some software restrictions imposed by Apple. Most popular reason why people do that is to get around only having to install apps from the App Store, which is a hard set restriction by Apple. But if you jailbreak your device, there is a dark store for apps for jailbreaking devices that couldn't get past the Apple week-long trial, and maybe for a reason. So something just to be aware of. You shouldn't be super afraid that people are going to do that, but just to be aware that people can do it. Apple actually gives advice on jailbreaking officially. It's not illegal. Their advice is mostly don't do it, but they do advise you if you have. So, quick recap. If the user shouldn't see it, don't send it via network request, do not ship it in the app code, and do not save it in Acing Storage. So you might be thinking, where the hell am I going to store my tokens then? Well, there are native solutions for this, which native developers amongst you probably know already. In Android, it's called Android Shared Preferences, and in iOS, it's called iOS Keychain. In both of these, you should still encrypt your data, because jailbroken devices can see that data in plain text as well. Now, if you want to, you can obviously access these directly and create your own bridge module, or non-bridge module in new React. But there are open source libraries that have done it for you and provide a nice API so you could use. So I think I've used both of these and they're fine. Haven't had any complaints. So in summary, do calculate permissions server-side, do only send user data that they are allowed to see, and use secure storage such as React Native Sensitive Info or React Native Keychain. All right, well, that's half the talk. Now let's talk about authentication. So in the olden days, every single app had their own authentication methods. So you had your usernames and your passwords, and then you have to hash the passwords and the usernames, and you have to reset the passwords and all that rubbish. And you have to, yeah. And we don't want to do that anymore. And a lot of the time we don't. So we use OpenID or Oauth 2. You've probably heard of both of them, and you probably think they're the same thing, but they're not exactly the same thing. So I'm going to tell you what the difference is. So I nicked this amazing graph from Slack because I thought it was pretty. There are a lot of these graphs around, and I never understand any of these. But in a very high level, the way this works is the application, which is your client or your mobile app, wants to obtain a token for the user so he could access resources. So it takes the client to a website where the client can log in. That is, grant authorization. Once the client is granted authorization, it goes back to their client with an authorization code. And this client then sends this authorization code to the authorization server, which goes, yep, that goes good to go. Here's a JWT token that will have the correct permissions. And then finally, you can use this JWT in your auth header and call whatever service API you wanted to with the correct permissions. Now, OpenID, you can almost think of it as a superset of Oauth in some ways, but it is an open standard and decentralized authentication protocol. So it allows users to be authenticated by cooperating sites. So rather than every single person implementing their own Oauth 2, they can use an already ready implementation by someone else. For example, you've definitely seen the sign-in with Google or Twitter or GitHub buttons. These are using OpenID Connect, which is authentication layer that sits on top of Oauth 2, which is why they look incredibly similar. So here's this in action in a React Native site. You press authorize, it opens a web view. This is logging into Identity Server, which is publicly available as a demo. So I'm putting in the username and password, logging in. Then I get to a page that you can choose which permissions to grant. So you could see that I could have unclicked the email, for example. And then you get the token and a refresh token. So you can refresh or revoke it. Now, this works really well in the web, and we've been using this for a while. But there are some problems with Oauth 2 in native apps. In fact, there is one particular quite dangerous security problem. But before I go into what that is exactly, let's look at what the requests look like. So this is the Oauth 2 flow. You can roughly put it in 3 steps. Number 1, we ask the user to authenticate. So we send a post request to the authorized endpoint with client ID, which is set up beforehand, the redirect URI, which tells the server where to redirect back once the authentication is completed, and scope, which is basically what the scope of a token is. So this is the bit that the user can choose to check or uncheck whether I can see their email or name or address, etc. So number 2, after a successful login, the user has put the username and password in correctly. They the authorization server redirects back into your app or to your website and gives the website the verification code. And then finally, in step 3, this verification code is exchanged for an Auth token with a token request, where we just provide the client ID, the same one that was provided in step 1, and the token code that was sent in step 2. Now, one of the things that's quite common if you use Oauth on the server side, but doesn't work on client side on web or on mobile, is client secrets. Now, if you're using an older Oauth server, a lot of the time client secrets are mandatory, and it's completely redundant in native because, as we just spent 15 minutes discussing, nothing is secret in native. So just to be aware, sometimes you have to include a client secret, but it means absolutely nothing. It adds no security whatsoever. But the actual problem relies in step 2. So after a successful login, the redirect URI is called together with the verification code. So that is the weak point of Oauth in the web, on mobile. So on the web, this is fine. You just go to a URL, it works. On native, though, if you're an Android user, you've definitely seen this pop up. This is if you've clicked on something, you're pressed on something, and there are several apps that are able to open this thing. You can choose from them, and pretty much the same thing can happen with the Oauth redirect, because the way that the redirect URI is provided on the web, it's a unique URI because all the URLs in the web are unique. However, on mobile applications, the same restrictions don't apply. So in this case, Chrome, Firefox, Internet, and YouTube can all open this particular intent. And at least on Android, you can choose, whereas on iOS, you will literally choose the first one that can open and will open it. So this leaves it open by an attack that's called Schema Squatting, which basically means that you can install a malicious application on someone's phone which listens to a call to that particular schema, and they can hijack your authorization, your auth code, and then use that to exchange for an actual authorization token, and then they've got access to your API infinitely. And we don't want that. So thankfully, the clever people that work on Oauth have added to the spec a thing called PKC or PIXI, which is called Proof Key for Code Exchange. So this is a security extension for Oauth 2, and it's designed to make Oauth on mobile clients secure. So let's look at how it works. Basically, what we do is in the authorize call, we add two additional parameters to the call. One of them is called a code challenge, which we create using a cryptography library. And the other one is a code challenge method, which is either SHA-256 or plain. And basically what we do is we are creating a hash, and we are sending that code challenge to the authorization server, as well as our authorization request. And then the other thing we add is when the verification code is actually exchanged at the very end, we send them the key that we use to generate this code challenge. And then what the authorization server does is it uses both the code challenge and the key and sees that if they match up, and if they do, they know that both of these requests came from the same device, well, the same app. Yeah, I mean, this is pretty simple, in theory, but it's hard to keep all that in mind. So there are libraries that do that. So the Auauth OpenID organization have both Auauth Android and Auauth iOS, which are native libraries for Android and iOS that handle the authentication, as well as PKC extension for all the clients that support it. And at Formidable, we also have a React Native Auauth, which is literally just a bridge for Auauth Android and Auauth iOS, which you can use for React Native. So the GIF that I showed earlier for the authentication, that's using React Native Auauth. And thank you very much. I hope you've had some security tips.